This work is based on a joint work with Jean-Louis from Metz and Karin Morita from Luxembourg. So we basically try to see, we try to look back the original classical result of Fourier inversion theory. Basically, if we start with locally compact abelian group G, and we know that whenever we take a L1 function defined on the group, which I denote by this small f, and we of course can take the Fourier transform of our L1 function, then we know that this Fourier transform of the L1 function will automatically be a L1 function defined on the dual group of the group. I just still keep this notation, although when the group is abelian, the dual group is still returned to the original group, but anyway, I will just keep my notation. Denote a head of G being the dual group of my original group. And then we know that from the classical Fourier inversion theory, basically just tells us that we can take another, again, the Fourier transform of our transform of the L1 function. This will give back to the original L1 function defined on the group. Especially if originally we take the L1 function is a continuous function, then this formula just holds for all elements from the group. So that's the classical Fourier inversion theorem. So our interest was, so now if we look at this classical result, and then can we ask if now we have just any locally compact group without the group being abelian, can we do something similar to the classical Fourier inversion theorem? But of course, in that case, I need to first explain what it means by the Fourier transform whenever my group is not abelian. So I will use the following notion by the Kirchhoff theorem in 1960. So from Kirchhoff's theorem, he said that now, say for example, if we look at the Nilpotent Lie group, so this from now on, my group will be a Nilpotent Lie group, and then there's a one-to-one correspondence between the dual space of the group with the co-adjoint orbits on the Lie algebra. So basically, what I mean here, it's not possible. So this is my Nilpotent Lie group, and then of course I can associate with the Lie algebra of it. And then what I mean here is that if I take element in the dual of my Lie algebra, then we can always associate with the orbit. And then what Kirchhoff says is that now we can actually have a function, denoted by this capital K, which really map this orbit. So basically, there's a map, which is a bijection actually, and map from any orbit of, or say the co-adjoint orbit on the Lie group, the Lie algebra, back into the representation on the original group. So this is a one-to-one correspondence map, and moreover, if apart from the group being nilpotent, if the group is exponential or even solvable, then in that case we know that this one-to-one correspondence is even a homeomorphism. So in many other cases, this K function can have very good property. So what we like about this, or what is important about this particular result, is that from now on we know that whenever we want to look at the representation on the group, which is basically the element our G hat, then we can view it as a co-adjoint orbit coming from the dual of the Lie algebra. So that's how it's one of the very useful tools for us. And then once we have this in mind, then I will try to explain what do I mean by the Fourier transform here in this particular case. Say if I pick up, from now on my G is just a Nilpotent Lie group. So if I pick up a Schwartz function defined on the group, then we can always look at so-called representation from our group. Basically, I just retake the induced representation from the group, reduced to the polarization of this particular orbit L with the character from my group. And then we know that from the classical result again, once we have a representation on the group, we can always lead it to the representation on L1 of G. So there's a natural correspondence between the unitary representation of the group, to the irreducible representation on L1 of G. So that's what I mean. Like I just use the same notation by this pi L. So this will give rise irreducible representation on L1 of G. And then we can also see that this when we look at pi L acting on the L1 function, this essentially can be viewed as an integral operator defined on the 1 of G. So I will just list precisely what I mean. So to be precise, simply means that if I take really a Schwartz function defined on the group, and if I take a vector from my Hilbert space, this Hilbert space of course is associated from the polarization of my list P of L. But in any case, I can really view my list representation pi L acting on the one function with this vector from my Hilbert space just as this operator, the integral operator. And if one write down precisely, then my list operator kernel is just really a function defined on the two variables from on G cross G. So now the question, so how we view it? We basically just really view the way how we take this the representation from the L1 function as the Fourier transform as a classical case. So basically, our question is that originally, if we start with L1 function defined on the billion group, we can take the Fourier transform, which gives rise to L1 function defined on the dual group. And then the classical Fourier inversion theorem tells that once I pick up any L1 function defined on the dual group, we can always take again the Fourier transform and then give rise back to the original L1 function defined on the group. So our question now is that if I just fix my group to be a Nilpotent Lie group, and then if I view this representation as the Fourier transformation, then can I start with any operator kernel function defined on G cross G, and then it can always return, or am I able to construct a map which will send back to the original Schwartz function defined on the group. Yeah, so this is what we mean by the Fourier inversion theorem on the Nilpotent Lie group. So that's exactly my question. So are we able to recover the original function defined on the group? Only start with our this operator kernel function defined on the G cross G. Moreover, is there any good correspondence between the Schwartz function defined on the group with this operator kernel function defined on the G cross G group? And this just really, I just write down precisely what I mean here. So now if I start with the operator kernel function, as I say, defined on the G cross G, and then can we re-specify what will be the Schwartz function with small f coming from the, whenever I add with this representation, this always gives back to the original, this operator kernel function. So that is really our question. And before showing the result we have, I will just briefly mention one known result. So Ho in 1977, he stated that basically he also had the same idea, try to look at whether there's a kind of Fourier inversion theorem for the simple connected Nilpotent Lie group. But what he did, he basically take the group Rn. So of course you can view it as a Nilpotent Lie group as well, and then he used some exact sequence technique and was able to have the following result. Basically says that if whenever you have an irreducible unitary representation on the group, so this group is again a Nilpotent Lie group, and then if you start with an irreducible unitary representation on the Hilbert space H pi, and also whenever you have any bounded smooth linear operator defined on the Hilbert space. So this is just my notation to mean it's not only a bounded linear operator, moreover it's a smooth bounded linear operator, because eventually we want to achieve that which can give rise to the original Schwartz function, which being a Schwartz function. So that's the reason we do ask some kind of smoothness of the operator. So once we fix also a smooth bounded linear operator on the Hilbert space, then there is always a Schwartz function defined on the group G, such that when you apply your reducible unitary representation on this Schwartz function, it always gives back to the original smooth bounded linear operator defined on the Hilbert space. So in a sense, this is really what we mean by the fully inversion property when you look at nilpotent Lie group. This really means that when I view my representation as a Fourier transform, then this indeed gives rise, it really gives you the relation between the operator and to the original Schwartz function. Moreover, what he showed also in his paper is that not only he can find this correspondence between the smooth bounded linear operator with the Schwartz function on the group. Moreover, he showed also that this correspondence is a continuous map, of course, with respect topology with Fourier topology when we talk about the smooth function on the group, the Schwartz function on the group. Also, when we talk about the smooth operator on the Hilbert space.
What do you mean by smooth operator here exactly?
So basically, this means that my operator will be differentiable in all the.
You seem to be defining it in a way that's independent of any choice of basis or something. So you have to be a little bit careful.
You mean the basis of the Hilbert space, or?
Yeah. Does this depend on the choice of a basis of the Hilbert space? I mean, these are.
It's not. Well, as far as I know, the result is independent from the choice of the basis.
Well, what do you mean by smooth then? I mean, these have to be. Something strange about the way you wrote this, because for one thing, if the representation were one-dimensional, then of course this map going in this direction has a huge kernel. I mean, even if it's not irreducible, even if it's not one-dimensional, the map going backwards could have a huge kernel because you're just looking at a fixed representation at a time, not looking at all the representations. And in general, for one of these representations defined by polarization, the operators that you get from a representation like this, that this B infinity is going to consist of, they're going to look like kernel operators that come from Schwartz functions on Rk cross Rk, right? Where K is the codimension.
Yeah.
Yeah. So they're compact operators with rapidly decreasing spectrum, but is
could you just explain briefly how you
how
define
you define
smoothness?
yeah. So what
How do you
mean by
find smoothness?
Yes.
Well, basically, I just briefly write down his result. But what we do, we really look for a sub-manifold sitting inside the Hilbert space, so that you can read. And then the function we define or the operator we define is really have the compassible sitting inside this manifold. So in the sense, you know that when you look at the, when you go to the boundary, it's just vanishing infinity. So the smoothness can be redefined on this submanifold inside the.
But is it intrinsic to the Hilbert space, or does it depend on the Hilbert space plus a particular parameterization of it?
But the Hilbert space, of course, depend on, in our case, this Hilbert space, of course, is depend on the polarization you take, right? So once if you pick up a particular element from the Lie algebra, then of course you associate with the polarization of it, right? So the Hilbert space is, of course, dependent on particular polarization of your element from the Lie algebra.
All right, we'll go on. I mean, something's a little strange about the way you wrote down this theorem. I mean, I know Howe's work very well, but
So what we try to do, so basically we just really try to construct such a, we call such a function called retract function, as I just mentioned before, that if once we have operator defined on Hilbert space, and try to see whether we are able to build a function, send this operator into a Schwartz function defined on the group. And then before going on the result, I will just briefly record what this list G invariant means. So basically what we want to do is that we want to define a so-called smooth G invariant manifold on the dual of the Lie algebra, and then which really have certain property mapping to the Schwartz function of the group. So what a subset of the dual of the Lie algebra means G invariant simply means that whenever I pick up any element from my subset of the Lie algebra, the dual of the Lie algebra, then we can really look at this action, which is really just element from the group acting on this element from the dual of the Lie algebra, and then it's just really the co-joint action on the group at the element from the Lie algebra. And as long as this action is still sitting inside the subset M, then we call this subset M is G invariant. So what we did with Sean and Karin is that now if we fix this G be a Nilpotent Lie algebra, and then we fix also a smooth G invariant submanifold of our dual of the group of the algebra, and then fix also it induce unitary representation whenever we pick up the element from our this smooth submanifold. And then what we are able to do is that we will be able to find open relative open subset sitting inside this submanifold of the dual of the Lie algebra, such that whenever we have any kernel function support really on the group acting on this relative compact subset of the submanifold, then we can really construct a Schwartz function defined on the group, such that when you apply the unitary reducible representation on the Schwartz function, it's really give rise to the starting operator f, the kernel function f. And then moreover, what we are able to show also, we really construct the actual function, and then from the construction, we are able to show that the map from this operator kernel to the Schwartz function on the group is indeed a continuous function, of course, with respect to the topology which satisfy the inquiry need. And what we did actually, how we prove the theorem, we actually do it a little bit more general than just prove this particular one. So in order to explain a little bit more, I need to introduce what means by a variable Nilpotent Lie group. So basically, we prove the results for the general variable Nilpotent Lie group by using the index, the notion of indexes, and also by using the induction on the length of the indexes. And then let's give us the result. So I will just briefly give a definition of what this variable Nilpotent Lie group means. So again, if I just start with a real vector space, which is just really my the algebra as before, and the dimension is fixed with this dimension n. And then if I start with a non-empty set, which is my beta, then this is my notation to denote the variable Nilpotent Lie algebra. So basically, I just really want to, whenever I have a variable, then I can associate each variable with a Nilpotent Lie algebra. So basically, the way how it can be done, just as following. whenever I pick up any element from my list non-empty subset beta, then I just associate with one D bracket on this original real vector space G, and then this will be my new notation. So basically, I start with the same real vector space. The only difference is that whenever I have different variable, then I associate with different Lie bracket, and then this G beta will be a nilpotent Lie group algebra. Secondly, this fixed Jordan-Holder basis for each of these G beta, but nevertheless have the following property. So basically what I mean in the second condition here is that this Jordan-Holder basis will be a fixed basis for the original this real vector space G, and then the only difference is that whenever you look at the different Lie bracket, this means that whenever I look at the different variable Lie algebra, then all the coefficients associated with the smaller indexes will give rise to zeros. So let's read the relation between the different vectors from the basis. So that's how we mean by a variable nilpotent Lie algebra, and then the original definition was given by Lupton and Ludwig in 1994. So they have studied quite a few different properties on the Lie groups using this variable nilpotent Lie groups ideas. And of course, once if you have a variable nilpotent Lie algebra, you can take the exponential of it. This of course gives rise to the variable nilpotent Lie groups. So that's the general result we actually obtain. So basically, instead of just looking at one nilpotent Lie group, we look at this variable nilpotent Lie group. And what do I mean by smooth? Simply means that, as I said previously, whenever I have a variable, I can associate with a nilpotent Lie group. So the smoothness here, I simply means that when I vary my variable from beta, then I want the variance between the different nilpotent Lie group is also smooth. Yeah, this is what I mean by the smooth variable nilpotent Lie group. And then now, because of that, as I said previously, I have a fixed Lie algebra for all these nilpotent Lie group. So that's still my notation. Then, as I said previously, if I have the variable nilpotent Lie group, of course I have the correspondence variable nilpotent Lie algebra. And then what I do now, I just fix a smooth G invariant submanifold in my list variable nilpotent Lie algebra. And then my extra condition is that I ask my list smooth manifold need to contain in a particular section. So basically means that once I start with this variable Lie algebra, then we can define an index on this variable nilpotent Lie algebra, so which is called the Ludwig Zaha indexes. So once we have indexes, and we're just really using the indexes to look at the different section on this variable nilpotent Lie algebra. So what the condition here simply means that I just ask my smooth submanifold need to contain in the section which corresponds to the lower indexes. And moreover, I also ask that whenever I look at the intersection of my list smooth submanifold with one particular section of my variable nilpotent Lie algebra, then I ask the intersection is non-empty. And once I have all these conditions, then I fix also a correspondence, or what I mean by here is just whenever I have a variable, then I look at the correspondence induced unitary representation coming from the variable associated with my list smooth submanifold. Then what we did is that just similar to the previous case. In that case, once we have all this information about the section from the submanifold with a section, then we know that we can always again construct or find an open relative compact subset sitting inside this particular section, which is again a manifold sitting inside this section. and such that for any adapt kernel function support on this G acting on the manifold, then we can construct a Schwartz function. Now the Schwartz function will be a Schwartz function defined on the variable Nilpotent Lie group. And what do we mean by the adapt kernel function? Simply means that apart from the original kernel function, we do need to have some extra property in order to have all this correspondence of the smoothness of the function. So basically, we ask that whenever I say a kernel function is adapt, this simply means that I also need some certain type of the property of my operator kernel need to be smooth as well on my manifold, such that whenever I have all this smoothness between the operators on this support, then in that case, we know that whenever I apply again my representation on the Schwartz function, is always give back to the original operator kernel I start with. And then similar result, we know that the relation between this operator kernel with the Schwartz function is again a continuous map between the two. There are quite a few there are technical conditions in order to really explain what really means by this adapt kernel function, and then also what really means by all these sections. But basically, because we take these variables, so in a sense, whenever we have a variable beta, we do have various these Nilpotent Lie groups, and then we do ask whenever we have a kind of functions or variables, we do ask all these functions and the maps and all the variables need to be smooth under certain property. So let's read the technicality which is needed in this theorem. And then as I say how we prove it, because once we have this variable Nilpotent Lie group, then as I said, we can adapt with index, and then we just count the length of the index, and how the proof was done just basically based on the induction of the length of the index. But yeah, because the proof was quite lengthy, so I will just skip it for now and then talk about the application first. So what is interesting for us about this result, not only provides a kind of this Fourier inversion theorem for the Nilpotent Lie group, moreover, this also helps us to be able to characterize what will be the prime ideal in L1 of G. So I will briefly first mention the correspondence and the needed definition. So now we will try to look at what is the G prime ideal of L1 of G. And then this broad G simply means that it's a subgroup of my automorphism group of the original Nilpotent Lie group. And then what G prime means? Now if I have a two-side closed ideal I sitting inside my L1 of G, then I say this ideal is G prime, simply means that this ideal I itself is G invariant. And then moreover, whenever you pick up any G invariant ideal I1 and I2 in L1 of G, such that when I take the convolution between two ideals containing in my original one, then either I1 need to be I or the I2 need to be I. So this is just really the classical definition of an ideal being prime. The only difference is that because now we work on a one function, so one function is closed under the convolution. So that's the only difference we take from the classical idea of the prime. And then we first observe that once you have such a definition of an ideal called G prime ideal, then you can see immediately that when we look at the kernel of each of the G orbit, then definitely the kernel of each G orbit is a G prime ideal. So basically, whenever you pick up any, as I say, this broad G is just really a subgroup of my automorphism group. So of course, it makes sense to talk about this G orbit. Then when you look at the kernel of it, it's just really full satisfied of this G prime ideal structure. So what we want to see is that, on the other hand, are we able to use the kernel of G orbit to characterize all the G prime ideals? So let's add some known results as well. So in 1803, Jean studied the closed prime ideal in L1 of G, which consists of the kernel of irreducible unitary representations. Again, the group here is Nilpotent Lie group, sorry. And then later on, Pogonke studied a bit more broad setting, which he looked at when there's a abelian compact group K acting on Nilpotent Lie group. And then he also tried to characterize the K prime ideals of the L1 of M. And then what he was able to do is that in this particular setting, and then all the K prime ideal are exactly the kernel of K orbit. But in his setting, he asked this group K need to be abelian apart from being compact. So the later result by Karim and her co-operator, they show that now if they relax the group K to be non-abelian, and they have similar results. So basically, now if I be a proper closed K prime ideal, and then K now is not only it's just a compact subgroup of the automorphism group, then they show that there is a K orbit. I just use the same notation as I had previously. So when they show that there is a K orbit, omega L, such that when you look at the kernel of this K orbit, intersect with all the Schwartz function coming from the group, this just coincide with the idea of intersect with the Schwartz function on the group. So basically, they have back then in a conjecture that they suppose that each of the proper closed prime ideal must be coincide with, or say, must coming from the kernel of the K orbit. This was their question back then in the paper. So what we show is that now we prove the result or the statement suggested by Karim and her co-operator, saying that now we start with just a simply connected Nilpotent Lie group, and then I just use the same notation, this broad G be a Lie group of automorphism on the group, and with one extra assumption that we just ask this broad G need to contain all the inner automorphism, such that whenever we look at the G orbit in the dual of the Lie algebra, and each of the G orbit need to be locally closed. And once we have this assumption, then what we are able to show is that indeed, whenever we look at the G prime ideal of one of G, then each of these G prime ideal is indeed coming from the kernel of the G orbit. So how this can be relinked to the original Fourier inversion theorem in our sense is just as the following. I will briefly give some notation and the idea of the proof to show you the link between this Fourier inversion and how to study, the study we have for the prime ideal in L1 of G. So we use this notation to denote this prim start of G, basically just a collection of all the kernel of the unitary irreducible representation from the group. And then whenever we have a subset in L1 of G, and we can talk about the whole of this I, and the whole is just given by the element from the prim start of G, such that this P is really contain our I. And then what we know is that not only from Kirchhoff's theorem, we know that there's one-to-one correspondence between the co-adjoint orbit on the algebra with the unitary irreducible representation on the group. Moreover, there's also a nice correspondence between the dual of the group with the prim star of G. So basically, we know that whenever I pick up a unitary irreducible representation on the group, then I look at the kernel of it, and this map is a homomorphism. And moreover, there's also the following few operations. So first of all, from our retract theorem, this basically means the full inversion theorem. What we know is that whenever we look at the kernel of the closed orbit and then intersect with the Schwartz function defined on the group, and if we take the closure under the L1 node, then this is actually coincide with the kernel of omega. So simply means that when we look at the kernel of orbit with the Schwartz function, this is really dense in the kernel of omega. Secondly, this is just observation from the prime star with the whole ideal. So what we know is that there is a minimum ideal denoted by J of omega sitting inside the Schwartz function of the group, such that when you look at the whole of this minimum ideal, this just return to the original closed orbit omega. And moreover, and then whenever you pick up any ideal of the Schwartz function with the whole sitting inside again omega, then we know that the whole of this omega is again containing in every ideal of the Schwartz function. So basically, how the proof can be done, we just really combine all these techniques and try to see that whenever we have a prime G ideal, and whether this is always coincide with, or is it always coming from a kernel of orbit. So the proof is done as following. So now if I start with, say this I is just a proper G prime ideal of L1 of G, then what we did first, we just take intersection with a Schwartz function. Then of course we know that this IS is just really a proper G prime ideal sitting inside my Schwartz function of the group. And then moreover, this is closed under the L1 node. And then taking some similar argument with Curring's past paper, what we can say is also that once we look at this particular proper G prime ideal in the Schwartz function, then we know that there is an orbit in this prime start of G, such that our this IS is just coincide with the kernel of this orbit intersect with the Schwartz function. Hence, when we look at the whole of our original idea, it's just the same thing as the whole of this idea intersect with the Schwartz function, and then I just replace my IS with the kernel of the orbit with the Schwartz function, and what we see is that the whole of the idea is just the closure of our orbit from the prime star of G. And then moreover, we know that our proper G prime ideal is also sitting inside the kernel of our orbit. On the other hand, from the retract theorem I just mentioned previously in the previous slide, we know that whenever I look at the kernel of the orbit intersect with the Schwartz function, this is really dense in the kernel of the orbit. And then if we just take the convolution of this kernel of omega with n times, then of course this is again sitting inside the whole of omega. And from the previous operation, again I showed the previous slide, this just again sitting inside our original proper G prime ideals. Once we have this statement, then we know that because I is a G prime ideal, right? So now if I is a prime ideal, then together with this inclusion, then of course what we can conclude is that our kernel of omega must sit inside our I, right? And then from our argument, of course we can show that our idea is just coincide with the kernel of the orbit we found from some other statements. So that's how we show that whenever we start with a proper G prime ideal on L1 of G, then we know that such an ideal is always coming from a kernel of a particular orbit from is the prefix of G. And I'm just repeating again the result we have. And as I say, the link between the study of the G prime idea of L1 of G with the link of it to the retract theorem or the full inversion theorem. Basically, once we have the full inversion theorem, this gives us the idea that whenever we look at the kernel of the orbit, intersect with all the Schwartz function, this is really dense in the kernel of the orbit. And then this particular key property is really coming from the full inversion theorem we have on the Nilpotent Lie. And that's how it helps us to calculate what will be the G prime ideal in L1 of G. All what I want to say.
Any questions or comments?
Yeah, so if you go back to the next to last slide, there's a key step which you didn't explain. Next to last?
The last
Yeah.
one, yeah.
Yeah. Right there, yeah, okay. So where does this, where do you get this capital N from? You need to, what you wrote doesn't explain what you did here. You want this kernel omega is going to be bigger than the J because the J is the minimal thing that has this property, right?
Yeah.
Yeah, but now you want to show that by taking a large enough power of this ideal, you can sort of shrink it down inside the J. So how do you do that? That's not something that's going to come for free. It's like a kind of spectral synthesis problem.
Yes, but exactly because we have this density of the. So basically, what I did is really using combine with these two arguments somehow. So first of all, we know that whenever I look at this kernel of the orbit, I intersect with the Schwartz function. It's really dense in kernel of orbit. Right?
Right.
And then moreover, we know that
But you're asserting something non-trivial, that you can find this n, so there has to be some formula for getting this n that has the property that when you take this large enough power, you can shrink the ideal down inside the minimal ideal. And that's not going to come from abstract nonsense. You actually need some estimate to do that. So that's what I wanted to understand.
we didn't actually need particular approximation to do that.
Well, then why, I mean, if you didn't need some particular estimate, then why wouldn't n equal 1 work? So, I mean, there has to be some argument here. That's what I don't understand. I mean, something strange, if this just came right from the last theorem, you wouldn't need to take the n, then the kernel of omega would already be in there. We're trying to use some kind of sandwiching argument, but I don't understand how this works. I mean, something's fishy about this.
We do use some past result of some synthesis of this, the orbit, the kernel of the orbit.
Well, also, you have to somehow use this assumption on capital G. Right,
Yeah, we ask G
yeah,
need
I mean,
to
if
come
capital
in
G were
order in
equal
a-
just equal to G itself, then this would be a little bit easier, but the capital G orbits can include more than one G orbit. And
we ask the broad G need to contain at least all the inner automorphism.
yeah, but if it's strictly bigger, then the capital G orbits are going to contain more than one G orbit. I mean, for example, a sort of stupid example, if G is abelian and capital G is the say G is Rn and capital G is GLN. Right, then the capital G orbits are huge. Right, there's one dense orbit and one and the origin, right? And then for the big orbit that the corresponding, the only corresponding prime ideal, I guess, is the zero ideal. But here, this omega, when you say orbit, you're using, I'm sort of confused. That word orbit is being used for two different things. So
Yeah.
they're the G orbits and the capital G orbits.
Yeah, so we are talking about the co-adjoint orbit.
Yeah.
So it's
So in the
from a
abelian
joint
case, the
action.
coadjoint orbits are points, but the capital G orbits could be very large.
But here I don't need the orbit from the broad G. What do you mean?
Because the capital J is
Is that
capital
ideal?
G prime, and the regular J is just ordinary G prime, right? And if the omega is just a point in the dual space, right? The omega here,
Yeah.
it's just a point in the dual space. So I'm just thinking about a sort of really stupid example. So suppose G is Rn, and capital G is GLN, and so the zero ideal is capital G prime and corresponds to the sort of big capital G orbit. And then you're saying that it has the same hull that its hull is the closure of a single point, and that's just not true. So something sort of wrong about the notation here, or maybe I'm misunderstanding the hypotheses of the theorem. What was the hypothesis on the theorem again?
We'll also ask this broad G needs.
Is a kernel of a capital G orbit, right? So but the capital G orbits have to appear in the proof, right? And in the way you wrote it, I'm confused about so that there are two different kinds of orbits here. There are the ordinary G orbits and there are the capital G orbits. And the proof has to use the capital G orbits. The capital G orbits, in general, are only locally closed. They're not usually closed.
Yeah.
And they can include lots and lots of regular G orbits. You could have more complicated examples where G is Rn, capital G is just any algebraic subgroup of GLN. So then, and this is sort of saying something like that these capital G orbits are all sets of spectral synthesis, which is a kind of non-trivial assertion, right? I mean, so even that case ought to be hard. That's what I'm worried about.
Probably I didn't understand you well what you mean.
Suppose the first G is just is abelian, but the capital G could be any it could be any algebraic subgroup of GLN, right? Then it will have locally closed orbits, which in general could be very complicated. And then the classification of the capital G prime ideals of L1 of Rn is actually a rather hard problem. And saying that they correspond to the capital G orbits is basically saying that these things are all sets of spectral synthesis, sort of in the sense of classical Fourier analysis. So this is not a trivial theorem by any means, even in the abelian case. I think it's true, but I mean, somehow or other, the proof has to use something harder.
Basically, how we prove it. Well, in the sense, the assumption for this broad G is really needed. In the sense, we do need to have this locally closeness in order to have better control of the orbit inside.
Right, yeah. Mm-hmm.
So, yeah, otherwise we don't know how to do it. So
Mhm.
the assumption indeed is needed. It's not really just for any subgroup of the automorphism group that we cannot do.
Right, yeah. No, I can sort of believe that, because for example, you could, even in the case where G is Rn, this gets really complicated, because the capital G could have orbits that sort of spiral into, you know, that could be really.
We also use some tool that was developed by other authors. They have better understanding how to control the orbit on the Nilpotent Lie group, and also look at this prim start. But they have a calculation there. So this is how we also use somehow. Our proof is actually not very difficult, because we use a lot of known results on the structure of the orbit they have done already. And also on this prim start of the Nilpotent Lie group. So they also have some known results how, when you try to look at this prim start of G, and then also try to look at this primitive ideal of L1 of G, or correspondent to the primitive ideal system algebra of G. And there are some known results, so we use some of the known results from there for the proof. So some of the technical idea you say that maybe it's already given there. That's why I want to really pay attention.
Anyone else have another question before we go back for tea and coffee? Okay. Time to speak.